title on screen, hands-on with confidential VMs, containers, and GPUs. My name is Skrzypek. This is Rey Lejano. We'll do an introduction slide, but I just want to make sure this is where you want to be. Like I said, we're just going to churn through content, so if you want to see one of the other tracks, feel free to leave now. As far as what we're going to cover in this talk, like I said, there's going to be a lot more content than there is time, and so I'll go over the high levels of what the workshop itself is supposed to accomplish, and then hopefully at a later date or maybe later today, you do the legwork and you go in, set up your own environment, and test things out to your heart's content. After I'm done going through the background and the quick run-through of confidential containers, Ray's going to chime in with some discussion and some architecture about confidential GPUs, and then we'll give some trailer slides as far as what you can do, ways to get back into, to contribute back to this open source. So I'll start first with introductions. My name is Skrzypek. As was alluded to in the last presentation, I actually am from Red Hat. I've jumped around several startups. I was at Red Hat back in the 20-teens, and I'll let Ray introduce himself.
Yeah. Hello, my name is Rey Lejano. I'm also a specialist adoption architect at Red Hat. I'm also more recently named Kubernetes maintainer. I've worked on 7 releases, been release lead from 123. I'm the maintainer for the upstream Kubernetes documentation, and I do lots of other things in the Kubernetes ecosystem. I've also been part of SUSE before and part of Rancher as well.
Yeah, if you need anything done in Kubernetes, reach out to this guy. He knows how to pull the strings. All right. So I have one liner as far as what is confidential computing. I would highly recommend that you look up the slide deck, which I believe is going to be posted. Okay, for the session that was immediately preceding this. But the main takeaway here is confidential computing is going to be that last data in category, the data in use. I didn't spend months figuring out the explicit definition, but that is still going to be hardware based. In this talk, we are going to do a lot of mocking. We're going to be doing things that aren't actually leveraging hardware-based confidential computing or encryption. But that's just so that if you're trying to explore this, if you're trying to unroll this out at your organization, you're going to be able to do that with just basic off-the-shelf laptops, with developer workstations, et cetera, et cetera. Again, this is a little bit duplicative of the previous session, but what we're really focusing here is a lift and shift of your current container workloads into perhaps an untrusted cloud provider's environment, or maybe in a multi-tenant situation where you want multiple parties that are mutually distrusting to interact with one another. There are several layers at which you can start applying confidentiality. Like I said, today we're going to focus on the topmost and the bottommost, the containers and the GPUs. But you also have at your disposal, you can set up your TEE around machines, you can set it up around entire clusters, and then test the various components therein. And so just as a quick high-level overview, we're going to talk today about installing a confidential runtime on a test Kubernetes cluster. We're going to set up an attestation service, and we're going to go through 6 different examples that kind of get you started on the path of interacting with something with confidential containers in the Kubernetes context. And then Ray's going to chime in with leveraging GPUs in confidential environments. Is there anything you want to add context-wise as a teaser?
Yeah, I'm actually going to more focus on GPUs and how to use GPUs in Kubernetes with a new feature called dynamic resource allocation. So that's going to be the primary focus of the demo later on.
Cool. So this is the slide that I wanted people to capture. This is my personal Git repository. It's shipwreck without any vowels, and it's /confidential containers. I'll give people a second to capture that information. All right. Seems like maybe one or two more pictures. Again, this will be available through Sketch if you want to click on the links. The repo's not going anywhere. If you go to that repo, you'll see that there's a fully fledged README. The README is going to talk about basically everything that I'm talking about today. There's going to be the architecture diagram. There's going to be several GIFs that actually go through the process of the demonstration and the installation. So if you don't like the sound of my voice, you can just watch this later, and you can see all the same content. The benefit of the way that we've structured this repository is that if you want to test it all in a predefined manner, something that you could just spin up without having access to different compute, you could just fork this repository and run everything in a code space. What's going to happen is it's going to spin you up an environment with all the preloaded tooling, the clients, all of the binaries that you need, and it's going to have a nice handheld script that will take you through what we're going to see. As an example, I have a code space up for this already. The script is going to pop up on screen in the terminal, and you can click on each of the options to go through the installation of that process. I definitely recommend going through it sequentially. I haven't tested it out of order. But if you want to just get to the point where your environment is fully set up with all the demonstrations, you can just click full send at the top. And then if you want to explore this environment or a couple utility functions, we have run K9s, which is a terminal-based UI for Kubernetes, and cleanup cluster if you want to just restart. Maybe you've screwed something up, or maybe you haven't tracked exactly what you've done. Okay, so the main reason why I built this presentation was because getting into confidential containing or computing, I had a lot of questions. There's a lot of different sources of information. You don't necessarily know how to get your hands on the different binaries, the different projects that are going on. And so I'm hoping that this can be the starting off point for a lot of people's exploration, and maybe get it adopted at certain organizations. Some of the main questions that we're going to ask, or a couple of the ones I'll point out, are, can I do this on my laptop? I'd like to commoditize the ability to test everything, and so I've made it available on laptops, like I said, in code spaces, in all of these different locations. How are secrets managed in these trusted execution environments or in confidential containers? There's a lot of examples in here of secrets management. And the last part that hopefully we'll get to is how is policy enforced or enabled in these environments? Those are the big three things here. So an overall view of what the demo environment has set up. The big yellow box on the outside is the host. This would be either your laptop or whatever cloud-based VM is running the code space. You have the container runtime. In this case, I think all of the code space is set up to use containerd. And then the purple box on the inside is going to be your container that is running your Kubernetes in Docker instance. In there, you have the four green boxes, which are going to be the namespaces. There's a default namespace, which is where we're going to do or put our tests. There's the trustee system namespace. Trustee is going to be the attestation service that we have access to in this cluster. We have the CoCo system namespace, which is going to be the namespace that contains all of the enablement of the confidential container runtime here in this cluster. And then, I got to fix that. Up at the top, there is an operator lifecycle management namespace. That's just going to manage the installation and updates of all these components. So if you had to productionalize this, you'd be able to do it in Kubernetes with a pretty standard productionalized way. All right, so we're going to skip through the actual process of setting everything up. I've done the television, turkey out of the oven switch. We'll go through the demos pretty quickly. But for confidential containers, the main takeaways here are there's going to be one main CRD, that is the CC runtime, and there's a link here. Basically, that's just going to make sure that when you want to run confidential containers, your Kubernetes cluster is going to know how to handle those requests. As you can see here, this one, the examples that we're going to do today are going to go through Kata agents, and the Kata runtime will be being promoted by QEMU. The second component that we're going to install that enables all of this is, like I said, the attestation agent. In this case, it is going to be trustee. Trustee is installed through the operator lifecycle manager. We're going to make use of a couple of the features, mostly that we're going to call for some attestation, but we're also going to use it as our secret source or a key broker service. but there's a lot more that you could do with it that you can configure with a KBS config down on the bottom. All right, and as far as the demos, which I'll go through the demos quickly here in text, and then we'll see them live, assuming I have time. We're 10 minutes in, right? Yeah. So demo 1 is going to be a simple pod definition. That pod definition is going to call out to a specific runtime class name. So there were questions earlier in the audience as far as how can we use the same container technologies but call out to a different runtime or add that confidential technology. And the way that we're doing it in Kubernetes is through this flag, the runtime class name. So when you provision a pod, it's going to go to the scheduler. The scheduler is going to say, well, I need these tools to implement this solution. I'll make sure that it's using this runtime. I'll get all of the verification that everything's set up the way it should, and then the pod goes into running, hopefully. And then demo 2. Demo 2 is where we're going to start to talk about some of the benefits of confidentiality. So as an aside, in confidential containers, your application still has the ability to completely nullify a lot of the value of the confidential computing. So if you have a web service that's calling out to an untrusted third party with the data, there's nothing that encrypting on that host is going to necessarily stop that from doing. And so one of the ways that you can enforce from a Kubernetes structure some policy on that workload is going to be with an annotation. And in the example of demo 2, we're restricting access to exact that container. We're going to be using Rego. You can see on the screen the actual key here is default exec process request equals false. And so when we run that workload, we're going to see that we can't actually exec into it. And so that's implementing that the administrators of the machines can't introspect what's going on in that environment. Demo 3 is going to be another smoke test to make sure that trustee is actually being leveraged. We're going to add some annotations. Those annotations are then just going to make sure that we have all of the networking components connected together. And then demo 4 is where we're going to start using trustee as our key broker service. It's going to allow us to store secrets, to make sure that secrets stay within our trusted compute base. Demo 5 is going to be trustee, but again, we're going to add a layer of policy so that only if we've attested successfully to a specific degree are we going to be able to access that secret data. And demo 6 is going to use something outside of, it's going to use different secrets mechanisms to access that secret data. In particular, we don't want to have to restructure our entire Kubernetes workloads to leverage confidential containers. And so in this case, we're using the Kubernetes secret store, the Kubernetes APIs. So if you do kubectl get secrets, that sort of thing. But we're keeping the exposure risk small because instead of storing the actual secret in that API, we're going to be storing a pointer to a secret that's stored in trustee. And so we maintain that small attack vector. Okay, and so now I'll switch over to my live environment. We'll do this one. So if anybody's unfamiliar, this is VS Code. I have the terminal on the bottom. I might reference some of the README on top, but most of the action is going to happen in the bottom. You can see that I've gone through and I've installed kind on the local machine. I've installed the operator lifecycle manager. I've installed the two operators that we need, trustee and the confidential containers operator, and then I've installed instances of each. So at this point, I have the ability to run containers. I have the ability to test things with trustee. So step number 1, as far as tests are concerned, we're going to do test runtime. It's going to apply that pod that is using that runtime. We can see that it's gone to ready, and then we can introspect that using K9S. So I've gone into the pod definition, and if we look somewhere down in the definition, all we've set to, there we go, that line 44 is where we call out to the Kata Kimu CoCo dev runtime, and that's, again, going into a VM as opposed to an actual container. We won't have time today to talk about how Kata implements the VM structures here. But basically, instead of using just containerd and spinning up a container, we have a more isolated environment. Demo 2 gets a little bit more interesting because we have policy enforcement. It's going to be the same pod. It's going to have that same runtime class. This time, though, we are adding a policy to an annotation. And if we want to look at that workload before we show that it's working, we can see that there's a lengthy encoded string at line 9 for the agent policy. If I were to decode that, what I would see is this long Rego policy. Like I said in the precursor, there's that default exec process request equals false. Because that is false, ideally, if everything's working correctly, we should have prevented any Kubernetes admin from accessing that workload. Oh, wait, and then I need to prove that I can't exec into it. If I press S here, normally in K9S, if I go to the previous workload, you can see that I have access to a shell. But on the new workload, if I try to shell into it, you can see it immediately bounces me back. The runtime is actually preventing me from executing here. We'll quickly do the test trustee connection, even though the artifacts there aren't too terribly meaningful. We'll just look at the logs of the workload and we'll see that it is actually calling the trustee service. The trustee service, as the architecture diagram showed, is running in trustee system. It's this trustee deployment. If I look at the logs, we should see a recent request that has successfully passed through. In this case, we're calling the KBS v0 attest endpoint, and the response code is 200. So we've successfully connected to trustee. Now that we have trustee, we will test a trustee secret. So this is not using the Kubernetes secret runtime at all. Instead, we are loading the secret into trustee, and then we're leveraging it from the annotations. We see that that's been successful. If we look at the workload, we would see the information as far as what the trustee service is, the 172.18.02. For anybody that wants to run this, this is just going to be the host IP because everything's running as a node port. But the important information here is we're calling localhost at port 8006 to /CDH, which stands for confidential data hub. And that confidential data hub API is going to be the way that we proxy out to trustee through the local machine. And then we're calling a default secret one secret. And if we check the logs, we should see that secret value. In this case, next example, we'll see the secret value. In this case, we've seen that because of policy that we haven't applied yet, we're getting a 500 error instead because trustee is blocking us from getting that secret because we haven't successfully attested. In this example, it'll go pretty quickly, but we're loading a new policy that uses our type of attestation in this case to say that our sample workloads using the sample runtime can access the secret. And so now, instead of being blocked with a 500 request or 500 response code, we should see, in this case, I do see an error, but we're going to forge ahead. But what we're supposed to see here is the super secret value, which hopefully we'll see in the next section. Last section here is this time we are going to use the Kubernetes API. That Kubernetes API is going to store a pointer to our secret as stored in Trusty, which I'm assuming if the last one didn't work, this one's not going to work for this demo. I do have this all pre-recorded, so I do recommend checking out the GIFs on the Git repository. Demos go the way that demos go. Yeah, and what we see here is a sealed secret value. That sealed secret value is, in fact, the pointer. The main contents of it that we would want to look at are this EYJ2X blah, 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 blah. If we go over to the repository, we'll see what that data actually is. Actually, let's look at this in Kubernetes instead. In the GIF that I've recorded beforehand, we can see that this is just a pointer to the KBS/KBS secret default 1, and that information is going to be loaded through the sealed secret mechanism into this cluster. I'll just make an aside here. If you're curious in seeing this actually run live before you take it into your environment and test it, I'll be available later today at the Red Hat booth. But on with Rey's.
All right, thank you very much. All right, so I'm going to really focus on using confidential containers, on how confidential containers could use GPUs with a new stable feature from Kubernetes called dynamic resource allocation, and that's the repository there. But first, I'm going to go over 2 ways how confidential containers can access GPUs. One is with confidential GPUs, and the other way is with dynamic resource allocation, is what I call the future of running AI workloads on Kubernetes. Just high level with confidential GPUs, it is very specific to CPU and GPU models. So this specifically for the NVIDIA H100 GPUs, which is on Hopper. The first supported CPUs were AMD Milan, then Intel Sapphire Rapids, and AMD Genoa. There's an Intel person in the room, so hopefully I am correct in that. But with confidential GPUs, it does have hardware logic so that it actually verifies the firmware, make sure that is vendor signed, so there's secure boot on it. Data is encrypted while it's being transferred from the GPU cores to memory, and the data is also encrypted using bounce buffers from data goes from the GPU to CPU. And just high-level overview on how confidential GPUs work in the public cloud, also on-prem. It utilizes several open-source projects here. So here is a diagram. We have the public cloud provider or a vendor like VMware hypervisor. Excuse me. There's a hardware IT, and there's also a confidential GPU. For AWS, this is your P5 instance that you would use. P5s have H100s. And here we're leveraging the PeerPods project. And the PeerPods project is able to invoke the cloud provider APIs or the VMware APIs to instantiate new instances, VMs or cloud provider instances, where you run your CVMs or your confidential virtual machines. Separate from the worker node, and PeerPods is typically set up on a separate cluster as well. So they're all separated out. So, like Jason mentioned before, we have the trustee operator for attestation in the key broker service. With the trustee operator, we also have a trustee agent running inside the confidential virtual machine. And of course, since the data inside the pod is encrypted, we need a way to decrypt that data. So we're going to use trustee with that. The trustee agent creates an attestation report from the hardware and software running in the hypervisor or the public cloud provider. It then sends that attestation report to the trustee operator. that trustee operator compares that attestation report to saved reference values that it does expect, and if it does validate it, it does release the key, sends it back to the trustee agent, which then sends it to the container to unlock it or decrypt it. But I'm going to spend some of my time here, since this is more of my focus is Kubernetes, especially with new Kubernetes releases. So back earlier this summer at KubeCon China and Japan, the CNCF announced a new conformance program called the Kubernetes Conformance for AI. So that was the alpha was released over the summer, and the first working doc has must and shoulds, and the very first must is that must support dynamic resource allocation instead of the device plugin. So some folks call it device plugin 2.0 instead of you. So we are in the very early stages, since it was just recently stable in August with Kubernetes 1.34. With dynamic resource allocation, you could request for resources with very fine-grained requests with common express language as well. And you could also share those resources amongst different pods as well. So a little diagram on with a confidential container using a GPU with DRA. So here in this diagram here, we have the DRA driver, which is from the vendor. So I do want to make a note that key contributors to the DRA feature is Patrick Oley from Intel and Kevin Clues from NVIDIA. So the DRA driver is from the vendor, is installed typically in the daemon set onto the worker node. It does create a resource slice, and the resource slice on the cluster is tied to that worker node. That resource slice has all the information about all the devices for that driver on that node. And it can often create a device class. That device class has all the configurations about those devices and is tied to the driver. Sometimes it is included with the driver itself, or your cluster admin has to create it. Keep in mind, this is all based on how storage is provisioned in Kubernetes as well. So very, very similar concept. So if you have produced or use storage in Kubernetes, instead of a storage class, there is a device class. With that, there's two ways to actually use a device or a GPU in Kubernetes using DRA. I'm going to go over two of them. Check my time here. First is a resource claim template, and the resource claim template references that device class, which then references that DRA driver. And if a pod, or if a pod running in a confidential virtual machine references that resource claim template, it will then create a unique resource claim that is tied to that pod. So it's tied to the pod's lifecycle. So when that pod goes away, same with the resource claim, which then references that device class, so we could use that DRA driver for that GPU. The second way of using a GPU with DRA is that you don't use a resource claim template, you just use a resource claim. So you have to create that resource claim separately, and the benefits of that resource claim can be shared among pods. So there's multiple ways to share GPUs, like with vGPUs, MIGs, time slicing, but this is also introduced another way of sharing GPUs as well, is to use resource claims. So now that unique resource, or now that shareable resource claim, it lives outside the pod lifecycle, can be shared by multiple pods. The DRA framework is not meant specifically just for GPUs, also for like for network attached devices as well. So since as we see the evolution of how devices are being used on-prem in the cloud, and how pods and Kubernetes can access those devices. So here's my demo recording. I'm going to go through the recording. It's a little slow, and there's a lot of kube control commands if you like kube control. Check my time. We're actually at time, but I think we will stay and answer any questions people have. And if you are staying, I will walk through this little tutorial. This is also in GitHub as well. So we're creating the namespace. For this part, we're creating that device class as well. In this case, the DRA driver does not creating that device class. So it's similar to a storage class. It just references that DRA driver. It does need some RBAC resources, just so we're creating a service account, the cluster role, and the cluster role binding as well. So those are 3 more resources here that's going to be created. that go through. And since things are in DRA are namespace as well, so just be aware. We are creating a priority class just to make sure there's no preemption for the DRA driver. Pretty soon here we're going to create the DRA driver, which is going to be a daemon set that we're going to take a look. But we're going to take a look at the driver first to just show you that is a DRA driver. This is an example driver, so you could actually use this to explore DRA on your local machine, even if you don't have a GPU. And throughout this demo, we're going to do some checks to make sure that that resource is actually being used by the pod. So it's very similar to how storage is provisioned to Kubernetes. So if you are familiar with the storage primitives in Kubernetes, then this will seem very similar as well. Any questions so far as this demo runs? So we're going to look at the resource slice. Like I mentioned, that resource slice is tied to the node. So if the node goes down, that resource slice also goes down as well. And we're going to take a look at this, this resource slice. This resource slice could also not just be satisfied just one specific GPU on a node. If a node has multiple GPUs, the DRA driver could actually be used for a category of GPUs as well. So here we are creating that resource claim. So in this case, now we have it in pending state, and in this resource claim, since we are using a resource claim, not the resource claim template, this resource claim will live outside the pod's lifecycle. And we're going to take a look at the pod as well before we actually create it. So we're going to see how it's referenced or how we reference that resource claim. So this is just, and also we are showing here how we are using the container runtime that Jason installed previously to make sure we are in a confidential virtual machine here. And here we are looking to the pod manifest to see where it references that resource claim. Now we're finally going to create the pod with keep control apply server side. I like server side because it makes sure that actually if there's any fields that are in conflict, server side doesn't have any conflict. So it does take a few minutes here, or a few seconds here. So now we want to make sure that the resource claim is used. So we check the resource claim, and now we see instead of pending, now it's allocated and reserved. And that is the end of the demo, and that goes into repeat.
So I know we're over time, so I'll just click through. We'll have questions afterwards if anybody wants to come to us. Please stay in this room. I mean, you can go get lunch, but come back for the consortium track. There's a lot of good content. And then, as always, open source works with everybody's contributions. There's a lot of links to the community, to different types of projects going on that you can contribute to.